Hi, I am Sumit Singh from Chemical Engineering Department at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. And today I would be presenting my assignment on the topic rate equation for fluid-solid catalytic reactions. These are the topics that we will cover under this assignment. First, we will go through the overview of this topic. Then we will study about rate of adsorption, then surface reaction, desorption, the rate limiting step in this process, what is power law, what is Langmuir-Hinshelwood rate, and then Eiley radial mechanism. Then we will study about packed bed reactor, then fluid bed reactor, and then we will see some solved numericals for our better understanding. One of the tasks of a chemical engineer is to study the rate data and to develop rate law which can be used in a reactor design. Rate law is usually different from what we study in our theoretical paper, and therefore we have to derive it from power law, which is a difficult task. Therefore, in order to derive rate law, first we study the mechanism of any process and then we derive the rate law. The mechanism for deriving the rate law typically involves adsorption step, a surface reaction step, and a desorption step, and one of them is usually rate limiting step, which determines the rate of reaction, the kinetics of the reaction of a process. A conceptual model depicting species A on the site is given below. Here we can see how a species A is attached to any site or surface. The reaction can be represented as A plus S is equal to A dot S, where A is the species or the atoms that is trying to attach on the site, S represents the surface or the site, A dot S represents one unit of A that which is adsorbed on the site S, and Ct represents the total molar concentration of the active sites, where Cv represents the molar concentration of the vacant sites. There are two models proposed for the adsorption of carbon monoxide on a metal surface. One in which carbon monoxide is attached as a whole molecule to any surface. So the reaction expression can be given as carbon monoxide plus surface is equal to carbon monoxide dot surface. And the other model in which carbon monoxide is separately attached as oxygen and carbon instead of a whole molecule. So the expression can be represented as carbon monoxide plus 2 surface is equal to C dot S plus O dot S. The former model is called the non-dissociative adsorption and the later one is called dissociative adsorption. Here in this diagram we can see both the examples. In the first one, carbon and oxygen being separately attached to the site of iron surface, and then in the second example, carbon and oxygen as carbon monoxide attached on the surface of nickel. First, let us consider the adsorption of molecular carbon monoxide. Since carbon monoxide does not react further after being adsorbed, we can write the expression as CO plus S is equal to CO dot S, and the rate of attachment can be given as Ka PCO dot Cv, where Ka represents the rate constant of the attachment of A to the site, PCO represents the partial pressure of the carbon monoxide vapor or gas, and Cv represents the concentration of the vacant sites on the surface. Then we can write a rate of detachment as K minus A into CO into the concentration of carbon monoxide and carbon monoxide that is being attached to the surface. So the expression becomes K subscript minus A dot C, concentration of carbon monoxide on the surface, and the total overall rate of adsorption we can obtain by adding the equation 2 and 3, where the final equation expression becomes rate of reaction of adsorption is equal to Ka into partial pressure of carbon monoxide into concentration of vacant site minus rate constant of detachment of A into concentration of carbon monoxide on the surface. The ratio capital Ka is equal to rate of attachment of A divided by rate of detachment of the species A, which gives us an adsorption equilibrium constant. And after rearranging the equation, we obtain the equation 5, that is Ka into PCO into Cv minus concentration of carbon monoxide on the surface divided by rate of attachment of A. And since carbon monoxide is the only material that is adsorbed on the catalyst or the site, the equation becomes the total concentration of the site or the surface is Ct, that is equal to concentration of vacant site plus concentration of the carbon monoxide that is already present on the surface. And this at the equilibrium, the net rate of adsorption equals 0. Therefore, when we equate the equation 5 to 0, we obtain the concentration of carbon monoxide on the surface, which is equal to the rate constant, equilibrium constant, into concentration of the vacant site into the partial pressure of carbon monoxide. And using equation 6 to give concentration of vacant site in terms of concentration of carbon monoxide, the total number of sites, we obtain equation 8, that is the concentration of carbon monoxide on the surface is equal to the rate constant into partial pressure of carbon monoxide into total concentration of the site minus concentration of carbon monoxide on the surface. And after rearranging the equation 8, we obtain the concentration of carbon monoxide on surface is equal to equilibrium constant into partial pressure of carbon monoxide into total molar concentration of the site divided by 1 plus equilibrium constant into partial pressure of carbon monoxide. Rearranging the equation 9 that we obtained further gives us partial pressure of carbon monoxide divided by concentration of carbon monoxide on surface is equal to 1 upon equilibrium constant into molar concentration of the total site minus partial pressure of carbon monoxide divided by the total concentration of site. And plotting this equation on the graph, we can obtain the graph, and thus the graph gives us the equilibrium value or the curve or the behavior of how this adsorption will take place. Now let us consider the second model in which the dissociative adsorption of carbon monoxide occurs. So the expression is given as carbon monoxide plus surface site is equal to carbon on the site plus oxygen on the site, where the overall rate of adsorption can be given as rate of adsorption is equal to rate constant into partial pressure of carbon monoxide into concentration of vacant sites squared minus inverse of the rate attachment A into concentration of oxygen on the site into concentration of carbon on the site. That is equation number 11. And rearranging the equation 11 gives us equation 12, where capital Ka is again represented as the ratio of rate constant of adsorption of A divided by rate of detachment of A. And further, when at equilibrium, we know that rate of adsorption is equal to 0. So when we equate the equation number 12 to 0, we can obtain equation number 13. Substituting the values of equation 14 and 15, we can obtain concentration of oxygen in terms of concentration of oxygen as rate constant A into partial pressure of carbon monoxide under the root into total concentration upon 1 plus 2 times the rate constant of A into partial pressure of carbon monoxide under the root. And then further simplifying the equation 16, we can obtain equation 17. And when we plot the graph of partial pressure of carbon monoxide versus the partial pressure of carbon monoxide divided by concentration of carbon monoxide, we obtain a linear graph or the linear curve, which again proves that our graph is linear. So dissociative model is correct, just like our non-dissociative model was correct. Now we study surface reaction, where we know how the species A is reacting on surface after being adsorbed on the site. So after a reactant has been adsorbed on a surface, there are only 3 possible ways in which it can react. So the first case is the surface reaction may be a single site mechanism in which only the site on which the reactant is adsorbed is involved in the reaction. For example, an adsorbed molecule of A may isomerize directly on the site to which it is attached. Because in each step the reaction mechanism is elementary, we can obtain the rate law as rate of reaction of S is equal to rate constant of S into concentration of A minus concentration of B upon rate constant of the site. The second case is as follows. The surface reaction may be a dual site mechanism in which the adsorbed reactant interact with another site. For example, adsorbed A may react with an adjacent vacant site to yield vacant site and the site on which the product is adsorbed. So our corresponding rate law becomes becomes Rs is equal to rate constant of S into concentration of A into concentration of vacant site minus concentration of B, the species B, into the concentration of vacant site divided by the rate constant of S. And we can easily summarize this whole reaction using this diagram. Then the other example of dual site mechanism is when two different species are adsorbed on the two different surface or two different sites. Then again with this diagram, this example is very clear and we can understand how the reaction is proceeding. And third dual site mechanism is as follows: when the reaction of two species adsorbed on different site S and S prime. So the rate law becomes rate of reaction of S is equal to rate constant S times concentration of A into concentration of B minus concentration of C into concentration of D upon rate constant S. Reaction which involves either single or dual site mechanisms which are described above are sometimes also known as the Langmuir-Hinshelwood kinetics. And the third mechanism is the reaction between an adsorbed molecule and a molecule in gas phase. So whenever the molecule is in gas phase, the rate law becomes rate of reaction of S is given as rate constant of S times concentration of A multiplied by partial pressure of B minus concentration of C into partial pressure of D upon rate constant S. And again in this diagram we can clearly see how B is reacting with the species that is already attached to the site and it forms a new product C and D. This type of mechanism is referred to as Eiley-Rideal mechanism. Now let us study how desorption of a reaction happens. So in each of the above case, the product of the surface reaction adsorbed on the surface are subsequently desorbed in gas phase. For the rate of desorption of species, example C, the rate expression is given as C dot S is equal to C plus S. By this reaction we mean that a molecule which has already been adsorbed and has reacted is now desorbing from the surface. So the rate expression is given as RD is equal to rate constant of desorption times concentration of C minus partial pressure of C into concentration of vacant site divided by the rate constant of desorption. So the desorption rate law can be expressed as RD is equal to rate constant of D times concentration of C minus partial pressure of C into concentration of vacant sites divided by the rate constant of desorption, where Kd is the desorption equilibrium constant. We note that desorption step for C is just the reverse of the adsorption step for C, and that the rate of desorption of C, Rd, is just the opposite in sign to the rate of adsorption of C. Therefore, rate of desorption of A is equal to minus times rate of adsorption of A, and therefore we can also say that the desorption equilibrium constant is just the reciprocal of adsorption equilibrium constant. Rate limiting step. Whenever heterogeneous reactions are carried out at steady state, the rates of each of the three reaction steps in series, that is adsorption, surface reaction and desorption, are equal to one another. Let us say minus Ra is equal to rate of reaction of adsorption, which is equal to rate of reaction of the surface reaction, which is equal to rate of reaction of the desorption. However, one particular step in the series is usually found to be rate limiting or rate controlling, that is the slowest step. That is, if we could make this particular step go faster, our entire reaction would proceed at an accelerated rate. Let us consider this rate limiting step with an analogy to the electrical circuit given below. In this circuit diagram, we can see that there are three resistances, that is the adsorption, surface reaction and desorption. Since we observe that total resistance is our task to find, and we know that total resistance is the sum of resistance of adsorption, surface reaction, and desorption. So our only task is to find which among the three is the highest resistance, and we need to minimize that resistance so that the current can easily flow through the circuit. Or in simpler terms, when we would minimize that resistance, our rate of reaction would proceed at an accelerated rate. Now let us study about power law, and how is power law different than the rate law that we generally study in chemical kinetics. So, power law is a functional relationship between two quantities where a relative change in one quantity results in a relative change in the other quantity, which is proportional to power of the change. In simpler terms, we are just relating to entities with power. So, for a simpler example, we can say a raised to power b is proportional to c raised to power d, where any change in C would give a change in A, which would be given by the terms of the power to which they are raised. In reaction engineering, this law relates the power of reactants in the rate law to the stoichiometry of reactants. For non-elementary reaction, power of the reactants in the rate law is not equal to the stoichiometric coefficient. Then this law comes into effect. A classical example of a non-elementary reaction can be taken as the reaction of hydrogen and bromine to produce 2 moles of hydrobromide gas. If the reaction would have been elementary, the rate of reaction would have simply been rate of reaction of HBr is equal to concentration of hydrogen times concentration of bromine. But since we know from the practical data that the reaction is non-elementary, so the rate expression is given as rate of reaction of HBr is equal to this the rate expression that is given. And this is because the reaction is not elementary, since it proceeds by free radical formation due to the breakdown of dibromine to monobromine due to photocatalytic reaction. Here our catalytic is the sunlight or the photocatalysis. Now let us study the mechanisms, different kind of mechanisms involved in the heterogeneous catalysis. The first one is the Langmuir-Hinshelwood mechanism, in which a species of A comes to the surface, it reacts, it migrates, it has a surface reaction, and in between it forms an intermediate product B, and in the final step it dissolves and form a final product that is C. And the second model is the Eiley-Radial mechanism, in which species A comes to the surface, it becomes an intermediate product and is immediately becomes a final product C. Both of these mechanisms can be clearly depicted in the diagram given. Now let us study the Langmuir-Hinshelwood rate mechanism in detail. This mechanism was suggested by Erwin Langmuir in 1921 and was further developed by Cyril Hinshelwood in 1926. The two molecules adsorb on neighboring site, and the adsorbed molecules undergo a biomolecular reaction. A plus S is equal to AS and B plus S is equal to BS. The overall reaction becomes AS plus BS is equal to product. The rate constants are now K1, K minus 1, K2 and K minus 2, which depicts the adsorption and desorption of A and the species B. The rate law is obtained as R is equal to K theta A into theta B into concentration of S squared, where the theta A plus theta B plus theta E represents 1, because these are the total mole fractions. Now let us assume that the rate limiting step is the reaction of adsorbed molecule, which is easily understood. The probability of two adsorbed molecules colliding is low. Then theta A is equal to K1 into concentration of A times the theta E. And thus our final rate expression becomes R is equal to K times concentration of S squared into K1 into K minus 1 into concentration of A into concentration of B divided by 1 plus K1 into concentration of A plus K2 into concentration of B whole squared. The rate law is complex and there is no clear order with respect to either reactant, but we can consider different values of the constants for which it is easy to measure integer orders. Both molecules have low adsorption. That means K1 K1 into concentration of A is smaller than 1, and the rate further simplifies to R is equal to rate constant into concentration of S squared times K1 K2 concentration of A concentration of B. The order is 1 with respect to each of the reactant and the overall order is 2. Now we have case 2 where one molecule has very low adsorption. In this case, K1 times concentration A is greater, 1 is greater than K2 times concentration of B, or this rate expression simplifies to R is equal to K times concentration of S squared times K1 K2 times concentration of A times concentration of B divided by 1 plus K1 times concentration of A whole squared. The reaction order is 1 with respect to B. There are two extreme possibilities for the order with respect to A. At low concentration of species A, the rate further simplifies to R is equal to K times concentration of S squared times concentration of A times concentration of B into K1 and K minus 1, and the order is with 1 with respect to A. At high concentration of the species A, the reaction expression simplifies to R is equal to K times concentration of S square times K2 times concentration of B divided by K1 times concentration of A. The order is minus 1 with respect to A. The higher the concentration of A, the slower the reaction goes. In this case, we say that A inhibits the reaction. And the last case is one molecule has very high adsorption. One of the reactant has very high adsorption and one doesn't absorb strongly. Therefore, K1 times concentration of A and 1 are greater than K2 times concentration of B. So the reaction expression simplifies as R is equal to K times concentration of S squared times K2 times concentration of B upon K1 times concentration of A. The reaction order is 1 with respect to B and minus 1 with respect to A. Reactant A again inhibits the reaction at all concentration. These are the following example where the Langmuir-Hinshelwood mechanisms comes into effect. These are common examples in the industry. For example, the reaction of carbon monoxide plus oxygen to produce carbon dioxide on a platinum catalyst, the reaction of carbon monoxide plus hydrogen to give methanol on a zinc oxide catalyst, the reaction of C2H4 and hydrogen to give C2H6 on a copper catalyst, the reaction of nitrogen oxide and hydrogen to give nitrogen and water on a platinum catalyst, the reaction of C2H4 and oxygen in a limited amount to give CH3CHO on a palladium catalyst, and the reaction of carbon monoxide plus hydroxide ion to give carbon dioxide and hydrogen and electron is on a platinum catalyst. Now let us study the Eiley-Riedel mechanism. In this mechanism proposed in 1938 by D.D. Edley and E.K. Riedel, only one of the molecule adsorbs and the other one reacts with it directly from the gas phase without adsorbing. The reaction expression is given as follow: A plus S is equal to AS, and AS further reacts with B to give the final product. The constants K1 and K minus 1 and K are the rate equation, and the rate equation is R is equal to K times concentration of S times theta A times concentration of B. Applying steady state approximation to AS and proceeding as before, we obtain the rate expression as R is equal to K times concentration of S times concentration of B into K1 times concentration of A upon 1 plus K1 times concentration of A. The order is 1 with respect to B. There are two possibilities depending on the concentration of reactant A. At low concentration of A, the reaction expression simplifies as R is equal to K times concentration of C times K1 times concentration of A times concentration of B, and the order is 1 with respect to the species A. At high concentration of species A, the reaction expression simplifies as R is equal to K times concentration of S times concentration of B, and the order is 0 with respect to the species A. These are the following example of reactions that follow highly radial mechanism, where example 1 is C2H4 plus oxygen in limited amount adsorbed gives us the product. The dissociative adsorption of oxygen is also possible, which leads to secondary product carbon dioxide and water. The second example, carbon dioxide and hydrogen reacts to give water and carbon monoxide. Then we have third example, the reaction of ammonia and oxygen to yield nitrogen gas and water on a platinum catalyst. The final example is the reaction of C2H2 and hydrogen to give C2H4 on a nickel or iron catalyst. Now let us proceed to packed bed reactor. A packed bed reactor, also commonly known as a fixed bed reactor, is essentially a tubular reactor which is packed with solid catalyst particles. In this reactor, reaction mixture is passed through the mass of a small catalyst particle. It consists of a cylinder of large diameter with multiple catalyst beds or many tubes in parallel packed with catalyst. This reactor makes use of relatively large size catalyst particles for lower pressure drops. These are the three common examples of the packed bed reactor that can be seen in the diagram. Now, how a packed bed reactor is designed, we must understand that, and therefore let us proceed further. The reactant, in this animation we can see that the reactant, the green ones, enter the reactor on the top and then flow through. Upon entering the reactor, the reactants follow through a packed bed reactor which is full of small beads of the catalysts, and by contact with the catalyst pellet, the reactant forms two product which is blue, represented by blue color, and then exit the reactor on the bottom. We can see the concentration gradient within the reactor. The color of the product from the green changes slowly to the color blue, which is the final product. When designing a packed bed reactor, we need to take in account the active life of catalyst. This will affect the length of time of a bed of catalyst may be used, and thus how long reactor may be run before the catalyst needs to be regenerated. The catalyst pellets that are used in the reactor are usually granular and ranges in diameter from 1 to 5 mm. They can be loaded into the reactor in several ways, as a single bed, separate shell, or in tubes. Catalysts are typically made from nickel, copper, osmium, platinum, and rhodium. The catalysts shown below are made of precious metal on 3.15 mm ceramic beads and are used in electric catalytic oxidizer that treats airstream contaminated with volatile organic matter that are known as VOCs. Now let us consider the usage example of packed bed reactor. These reactors have wide range of use of catalytic reaction. They are also widely used in small scale commercial reaction. In this table, we can see the advantage and the disadvantages depicted for a packed bed reactor. Advantages include high conversion rate per weight of catalyst. They are easy to build and maintain. The more contact between reactant and catalyst occurs, so the reactant has enough time to react with the catalyst. More product is formed due to increased reactant and catalytic contact. Again, low cost of construction, operation, and maintenance, and they are effective at high temperature and pressure. But on the other hand, disadvantages include they are difficult to control temperature. Temperature gradient may occur. For example, the reactor may be very hot in some areas and may be cold in some areas, due to which the product may not be uniform. The catalysts are difficult to replace inside the reactor. Channeling of gas streams may occur, leading to ineffective regions in the reactor. Then side reactions are also possible, which can reduce the efficiency of reactor. Heat transfer from reactor can be difficult to study. Now let us study about the fluidized bed reactor. This is analogous to the continuous stirred tank reactor in that its contents are though heterogeneous and are well mixed, that results in even temperature distribution throughout the bed. It consists of a vertical cylindrical vessel containing fine solid particles. The fluid stream, which is usually gaseous, is introduced to the bottom of the reactor at rate such that solid are suspended in the fluid stream. These are the three examples of the fluidized bed reactor of different kinds that are used in the industries. Now let us consider the design of a fluidized bed reactor and how it is built and constructed. Before in this animation given, we can clearly summarize how the fluidized bed reactor operates. Before the reactor is started, catalyst pellet lie on the grate at the bottom of the reactor, and as soon as the reactants are pumped into the reactor through a distributor continuously, causing the bed to become fluidized. The bed's behavior after initial fluidization depends on the state of the reactant. If the liquid, the bed expands uniformly with increased upward flow of the reactant. This is called homogeneous fluidization. If the reactant is a gas, and bed will be non-uniform because of the gas forms bubble in the bed, results in aggregating fluidization. During the process, reactants react due to the presence of the catalyst pellet, forming products that are removed continuously. And basically what we mean to say is that the reactant comes enter the reactor from the bottom zone and leaves from the upward zone, and in middle it reacts with the catalysts which are suspended in the fluid or the gas form. Fluidized bed reactors are generally very large, and they must be designed so that the fluid flow rate is sufficient so that the catalyst particles remain suspended. The catalyst particle size typically ranges in diameter from 10 to 300 microns, which is very very small in size. When designing fluidized bed reactor, the catalyst must also be taken into account. Most of the fluidized bed reactors, such as the one shown here, have a separate compartment to regenerate the catalyst. Let us consider the usage example of fluidized bed reactors. These reactors are commonly used in catalytic cracking processes. These are also used in the roasting of sulfite ores, coking of petroleum residues, and the calcination of limestone. They are often used when there is large need of amounts of heat input and output, or when closely controlled temperatures are required. The advantages are listed as below. Even temperature distribution eliminates hot spots. Catalyst is easily replaced or regenerated. It allows for continuous and automatically controlled operation, and plus more efficient contacting of gas and solid than in any other catalytic reactor. But let us also consider the disadvantages. It is expensive to construct and maintenance cost is high. Erosion of reactor wall may occur. Regeneration of equipment for catalyst is expensive. Catalyst may be deactivated. Can't be used with catalyst solids that won't flow freely. Large pressure drops. Attrition, breakup of catalyst pellets due to impact against reactor wall can occur. In order to choose between packed bed reactor and fluidized bed reactor, we need to know their differences so that it is easy for us to know how they perform. So this table represents the differences between the two reactors, and based on this data, we can easily decide which reactor we need to choose for a specific process manufacturing. Let us consider a few numerical questions in order to have a clear understanding of whatever we have learned. So here is the first question. How much catalyst is needed in packed bed reactor assuming plug flow for 35% conversion of A to R for a feed of 2000 mole per hour of pure gaseous A at 3.2 atmosphere and 170 degrees Celsius? So first of all, we need to use the concept of plug flow behavior and the performance equation, from where we have obtained the rate expression in terms of concentration of A. After finding the concentration of A expression, we need to put that into the performance equation and we need to integrate. After integrating, we obtain the equation as W is equal to Fa naught upon K into concentration of A times 1 plus E 1 plus E times A ln 1 upon 1 minus XA minus E times XA. From this equation, we find, after putting the values of all the data, we can finally obtain the W value or the amount of catalyst needed in the packed bed reactor to be 139.41 kg. Let us consider one more example. How much catalyst is needed in packed bed reactor with large recycle rate for 35% conversion of 2000 mole per hour of pure gaseous A at 3.2 atmosphere and 117 degrees Celsius. So in this question, we need to find out the rate expression in terms of concentration of A, and then after we found the concentration of A, we can put that into the performance equation and finally solve the overall expression to find out the overall expression, which is equal to W is equal to Fa naught times XA times 1 plus Ea times XA divided by K 1 minus XA times concentration of A. And after substituting all of the data that we have been given, we obtain the amount of catalyst that is required for this particular reaction is 229 kgs. Thank you.